All right, so starting chapter 3, what we were just talking about earlier is the last two chapters are very review, pretty much exclusively content out of 105, 106, maybe a little bit more depth, but it's all based on familiar things. We're going to start this chapter with nomenclature, kind of just the language around naming things and some of the basics of hydrocarbons. And then at the end of this lecture, we're going to get potentially into Newman projections and analysis of the degree of freedom of rotation of different single bonds. And then next lecture, we're going to spend the vast majority of the lecture on cyclohexane conformations and what they look like three-dimensionally and how to predict which of all the different possibilities are preferred based on where the substituents are. So synapses, it's about to get really unfamiliar really fast, so get ready to, in the next week and two, you're officially like in OChem for real. Not that you haven't been doing OChem so far, but it's going to be more so. So let's see here. So for majority of this semester, we're going to be looking at just a couple different types of functional groups. We're going to be looking at
Am I all dead already? There's a black one on the edge.
We're going to find out here. Maybe blue's pretty. We're going to be looking at alkanes, which we're going to start with today. Alkyl halides, which are when we have halogens substituted on alkanes. We're going to look at ethers, alcohols, and amines. So this is where most of our energy is going to be for the rest of the semester, and then when we start next semester, it'll be benzene rings and aromatics, and carboxylic acids, and esters, and other things. So, but this is where we're going to have most of our attention this semester. So, naturally, what we're going to do today is just the way a lot of books organize things is they won't talk about nomenclature for alcohols until we get to the alcohol chapter. This book gives you nomenclature right out the gate for all of these. In some ways, that's harder because it's more nomenclature and there's some little differences and subtleties. In some ways, it's better because you get to focus on it all at once. Now, heads up when it comes to nomenclature, and we're talking about how we name things so that you can draw a structure from the name. This will haunt you for the next year if you don't learn it well. I know because I learned it just passably as an undergrad. And by passably meant I passed the first test. And then it's like, oh, well, that's gone. Thank goodness. But then it kept coming back because all of these, there was this expectation that you would be able to draw the structure from a name or communicate a name from a structure. And that didn't go away for some reason. It just kept coming back. So every test, I was eating points because my nomenclature was terrible. And I tried to find the help from the grad student, and she's like, I don't do nomenclature. I'm just here to shim the NMR. She couldn't do it either. So, because she wasn't teaching the class, to be fair. But this isn't that hard, but it's the kind of thing that if you only cram it in and then you never re-practice it, it will become a source of angst for you throughout the rest of your organic chemistry career. So what I'd recommend doing is revisiting simple nomenclature problems periodically just so that it stays comfortable. Let's see here. So let's start with alkanes. We're not going to jump into nomenclature. I have a few definitions first. So an alkane is any compound which is composed of carbons and hydrogens, and sometimes they're modified, but we have different names for those modifications. So for right now, alkanes can just be carbons and hydrogens. And in this case, there's another qualification. It's all single bonds. because if we had a double bond now, it's an alkene. If we had a triple bond now, it's an alkyne. By definition, because we've added these things that are more reactive than the single bonds. So if you hear alkane, you know it's all single bonds. So there's a couple different variations on this. The simplest versions are straight chain. And then we can also have branching. And as we get larger and larger and larger compounds with more carbons, you're almost always going to see branching to some degree. So this is not the exception to the rule. What straight chain looks like is, let's see here. Well, let's just do the homologous series. So a homologous series is just a series where we're adding a carbon sequentially to something of the same chemical identity over and over and over. So for our most simple straight chain alkanes, we've got one carbon, we've got two carbons, we've got three carbons, four carbons, etc. And we could draw this as, well, you don't see a lot of skeletal formulas for ethane because it looks like this. That's pretty boring. Usually you'll see CH4, you'll see CH3, and then we can start to do stuff like this for propane, this for butane. So you got names. Every alkane is named ane to identify it as an alkane, and has a prefix which tells you how many carbons are part of the chain. So in this case, the prefix for one is methane, ethane, propane, butane, pentane is 5, 1, 2, 3, 4, 5. Hexane, 1, 2, 3, 4, 5, 6. Heptane, octane, nonane, decane. And the book goes into some of the higher order ones, like the teens and 20s, but I'm not going to ask you that. You guys don't have to commit that one to memory unless you really, really feel like it. But important thing here, we've got one carbon, two carbon, 3, 4, 5, 6, 7, 8, etc. So obviously you're going to want to get super comfortable with the prefixes: methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, decyl. That's just going to be part of the language. One of the things that throws people in the first exam, sometimes a question will say, how many secondary hydrogens is in X compound? And it names the compound. So the first part of the problem is you have to be able to draw the compound from the name correctly, so you then can identify how many of a certain type of hydrogen are present. So people are like, "What? I don't get the structure." It's like, "No, you do. You got the name, which gives you the structure," which is kind of mean of me to say it like that, but it's true. So get super comfortable with this. In terms of structures, there's only one way we can draw methane. Methane is going to look like this, because there's only one carbon and we have 4 identical atoms attached to that carbon. So methane is going to be methane is going to be methane as a category. Ethane, very similar in terms of complexity. And we'll find at the end of this chapter that we can have some freedom of rotation around that bond, but ethane is ethane is ethane. Propane is where it starts to get a little bit interesting. Propane itself has just 3 carbons, so there's only one way you can put that together because you have a central carbon. So because we have a central carbon, propane will look like propane will look like propane. But if propane is being used as a substituent group, meaning we have some large compound, or let's say we have, say, a benzene ring, we can have a propyl group that looks like 1, 2, 3 attached to it. CH3, CH2, CH2. Or we can arrange those 3 carbons differently. And attach the functional group, or excuse me, the substituent at a different carbon in the chain. So this starts to get us some increasing complexity because we're adding carbons. This is an isopropyl group, whereas this is just referred to as a propyl group. So this is a common name. We could also name it 1-methyl ethyl and use nomenclature rules to identify it, but nearly everyone's going to look at that and go, well, that's an isopropyl group. And you can name it using the common name almost always, unless it's specifically asked for the rules-based name in the question. And let's see what happens when we add another carbon. So with butane, with only 4 carbons, we have 1, 2, 3, 4 carbons possible. We could also have something that looks like this. This has 1, 2, 3, 4. So notice terminal methyl groups. This would be a CH2. This will be a CH2. This would be a CH with 3 methyls. Same thing, just a variation on what butane is, but very different chemical or distinct chemical properties. So this gets even more complex as we start to do butyl groups. So if we're doing, let's see here. We could have something where we have just regular butane, 1, 2, 3, 4 as a butyl group. We could have 1, 2, 3, 4, or 1, 2, 3, 4. So now we have an extra layer of complexity just from adding that other carbon. For each carbon we add subsequently, the number of variations on ways we can arrange things to fit 5 carbons, 6 carbons, 7 carbons gets more and more and more complex. So around this point we run out of common names where we can call this isobutane and this another variation on butane, regular or butyl groups. But you're going to run out of room really fast for common names. So pay attention to the common names in the chapter, but you should always be able to just name these from rules if you forget a common name as well. So let's see here. Let's start talking about...
Professor?
Yes?
Oh, I have a question. So on the one to the far right,
Yes.
and you said that was a butyl group?
Yes, because we've got this R group. Let me.
Oh, okay, that's the R group.
So this is the R group.
Okay.
So this is the main thing that is being named, and then this is a substituent attached to it. So we've got our CH3, CH3, CH2, CH.
Okay, great. That's a little bit clarifying. I had a question about
Clarifying. I think you said terrifying for
Oh,
a second.
okay.
Okay. Okay. It's not that bad yet. Okay.
So say you have an R group that's a chain.
Mm-hmm.
What is a good rule to differentiate the substituent?
We will get there when we're identifying what the main chain is. Just a second. One other thing that we want to pay attention to is different classifications of carbons and hydrogens, because they'll have different chemical properties. We're going to be categorizing carbons as, and hydrogens, well no, just carbons, primary, secondary, tertiary, quaternary, and hydrogens can be primary, secondary, or tertiary. What defines a hydrogen as primary, secondary, tertiary when it's attached to a carbon is whether the carbon is primary, secondary, or tertiary. If the carbon is primary, it's going to house primary hydrogens. If it's secondary, it will house secondary hydrogens. So super simple to figure this out if you know what this is. The reason there's no quaternary is because quaternary carbons have no hydrogens attached to them by definition. So if you're ever asked to identify the number of quaternary hydrogens on something, it's a trick. Don't spend that much time trying to figure out whether it's a trick or not. It's a trick. So, let's see here. Primary carbons, 1, 2, 3, 4. This is a primary carbon because it has a single carbon attached to it, by definition. So, because this carbon is connected to a single carbon, it's primary. This carbon is secondary because it's attached to two carbons. This carbon, use all the markers today. Ooh, that's nice. It's tertiary because it's connected to 3 carbons. Each of these has, and what you also get fast at is saying, oh, well, there's 3 hydrogens, so primary, 2, secondary, 1, tertiary. So this hydrogen, these 3 hydrogens, because they're attached to a primary carbon, are primary. These 2 hydrogens attached to this secondary carbon are secondary. That hydrogen attached to the tertiary carbon is tertiary. In terms of quaternary carbon, what does that look like? So you've got a carbon in the middle of something like this, where you have 4 carbons attached to that carbon, so all of its possible bonds are to other carbons. This one's quaternary. And the book doesn't, I think, discuss quaternary yet, but there's no reason not to include it. And once again, because there's no hydrogen attached to it, quaternary hydrogens aren't a thing.
Does that only apply for carbon? So like, what if one of those was an alkane? Would it still be?
Oh, we'll get there. Yeah, when we get to this you have these prescient questions. Another question.
Oh, I had the same question.
Oh, okay. Okay, no, we'll be getting there because alcohol's very similar, and then as soon as we get to nitrogens, everything's going to get flipped on its head for some reason. Yes.
So, let's say, like, is the first degree hydrogen one that's like
Primary.
all right? So CH3, those are those are primary hydrogens.
Yes, because they're attached to primary carbon.
All right.
Okay, so let's do some actual naming of things now that we've got it. Oh, we have another one.
It was just a question. I was just wondering, it doesn't, so the primary, secondary isn't determined by like how many along it is, just how many it's attached to.
Right.
Okay, so CH2 on the end would still be primary.
This one?
Yeah. It's attached to one.
Because this is probably not the best example because I'm throwing an alcohol in here.
He's secondary. Okay.
It's going to become important when we're talking about carbocation stabilization because primary, secondary, tertiary, quaternary carbons will have different affinities for holding positive charge based on delocalization. So it's really about the number of groups they have attached to them more than the place they are in a chain. And the reason the hydroxyl isn't the best example here is because its electron withdrawing is going to change some of that a little bit. But like I said, we're going to be getting to alcohols in a second, so that's a good question too. Other questions? All right. Okay, so nomenclature around alkanes. So the first thing you have to do is find the parent chain. So this is the longest continuous chain. And you have to be careful of perspective in the way chains are displayed. So let's say you have something like this. The longest chain would include 1, 2, 3, 4, 5, 6, 7 carbons. So this would be a heptane. Is it still a heptane? Yes. Because now the longest continuous chain is 1, 2, 3, 4, 5, 6, 7, 8. So now it's an octane, and these are no longer part of the continuous chain. So in something, you'll see some structures that look like these when we're doing terpenoid pathways later. And you'll start to question what the longest chain is based on where things are folded. So just make sure you're paying attention to how things are folded, because it's not always going to be this if we have some larger substituent groups hanging around. So. Yes. I can draw stuff again.
I just didn't understand. I thought it was still longer the other way.
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8.
I had it.
No problem. Okay, so that's 1. 2, number and name alkyl substituents. So for these examples, until we start adding other functional groups for substituents, we're going to stick with all alkyl groups because it's the easiest place to start. alkyl substituents, we've already kind of discussed it. It's when another alkane is used to modify the parent chain, but it's small enough and placed in a way where it's not changing the identity of the parent chain. So this here will have a parent chain of 1, 2, 3, 4, 5 carbons, so it's going to be a pentane, and this will be modified by a single alkyl group. And when you do this, instead of methane, because this is a methane that's modified as an alkyl substituent, the ane falls away and you replace it with il. So this is by definition how you treat modifying an alkane to an alkyl group by name. Yes?
Why is that not a
1, 2, 3, 4, 5. Pentane? Did I not say pentane?
Yeah, you said.
I thought pentane. If I'm a little wonky today, I had a vertebra very badly out over the weekend, so I spent a majority of the weekend slightly modified. And I'm not right now, I think, pretty sure, but I'm still a little foggy. Yes?
So is that called then methyl or?
Oh no. 1, 2, 3, 4, 5. So what we'll do here is you number and name the substituents. So how do we number? There's all kinds of rules around numbering, but we're going to number, for now, from the side that gives you the lowest number for your substituent. In this case, I could have numbered from either side and gotten the same number here because it's symmetrical, but you wouldn't always have a symmetrical scenario. So this will be 3-methyl pentane. So you name it as you name the parent chain is the base of the name, and then you modify this, identifying where different substituents are. Had a question? Yeah.
So if you had another substituent on 4, would be like 3-methyl 4-ethyl.
Opportune question.
The heptyl would be longer, so would that be that?
If I did this,
Well, then that could be part of the parent chain then.
but it's symmetrical, so it doesn't matter. Either one can be.
Yeah, okay.
It's arbitrary. But if I did this and made an ethyl group, then that would make a longer parent chain. We'd have 1, 2, 3, 4, 5, 6.
Yep, so then you have.
Right. So then this would be by definition, a methyl group modifying it. But it's an opportune question because that's the next thing that you do. So if you've got more than one, if you have more than one substituent, what you do is you number so that you have the lowest. Okay. You always start numbering from the side that has the closest, unless they're the same. And if they're the same distance from the ends of the parent chain, you start on the side that gives you the lowest total of your numbers. And then what you do is, in the name, you list them alphabetically. Whenever I do the little alpha, that's just shorthand for alphabetically. And if you have multiples of the same type of substituent, use bi, tri, tetra, etc. So let's do some examples of that so it makes sense. Yeah.
Is the di ever used versus bi?
Di? Are they using di?
I think it's
Di?
using
Bi, di.
Bi.
Di, tri, tetra. Di. Oh, let's see, bis. Dimethyl, not bimethyl. It's dimethyl. It's di. Glad you guys are on it today. So let's do an example of this. Let's say we've got 1, 2, 3, 4, 5. Let's say we've got this compound, parent chain. These are symmetric here, so I'm just going to stick with 1, 2, 3, 4, 5. It could be 1, 2, 3, 4, 5. The reason I'm numbering from this end is because the first substituent is nearest this side. So this is going to be a 2-methyl. This is going to be a 3-methyl. Because we have two of the same type, it's not going to be labeled 2-methyl, 3-methyl. It's going to be 2,3-dimethyl. So this is going to be 2,3-dimethyl pentane. Let me do one more. It might clarify. If we have, let's see here, heptane 1, 2, 3, 4, 5, 6, 7. Let's see here. What about that one? Does it matter if we include this group here or this group here? They're symmetric.
Yeah.
And same thing here. So which side should we start from? From the right side?
The left.
Well, it's the left because it would have the smallest.
But you start from the side that's closest, right?
Closest to your substituent.
So, substituent, substituent, substituent.
I said left.
But this substituent is closer to the end than this one or this one by a carbon. So that's the first rule. If they're identical, then we have to go to the addition rule. Yeah.
Are these rules all in the book?
Yeah. Yes, they are. They might have a slightly different numbering scheme, but they're all in the book. So this would be, how many methyls do we have? 2. So we have a 2,5-dimethyl, and then we have an ethyl. So the di-tri doesn't factor into the alphabetical component. So methyl ethyl, which one comes first as being listed? Ethyl, because it's alphabetic. So this is going to be a 5-ethyl, 2,5-dimethyl. How many we got? 7 heptane. The numbers don't go in order exactly, necessarily. Yeah.
Is it possible to have more than 4 of the same substituent on a chain? Say if you have 5 or 6 methods?
Sure. I could do that off the top of my head. I could make one of those up.
Because then you can't use di, tri, or tetra.
Bam, 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 bam.
Cool.
But the dyes, it doesn't count.
So yes, it's possible. But there's more, but it's rare.
What about, like, let's say you added another methyl group onto the 2, what would it be then?
Like here?
Yeah.
That would be a 2,2,5 trimethyl.
So you would include the 2 twice?
Yes. Because otherwise you wouldn't necessarily know if the third one was on a 2 or a 5.
Why is it, you said it before, but why is it you start from the right instead of the bottom one?
Because the first substituent is closest to the end on that side. The sum of making the lowest possible number only matters if you don't have a clear. So let's see if I can come up with a.
So it's not written in the rules.
Let's see here. Oh, that's a more complex question. Yeah, this one, we don't have a rule for that yet. Sorry. Let's keep adding rules, because as we add more complexity, it might help solidify some of these scenarios.
But one of the rules that should be up there is that for numbering, start from the place where the first constituent would be closest.
That's when I was talking about here. When I was talking about number and name alkyl subs, I talked about you always number from the side where the first substituent is closest. This is in the absence of having a lowest substituent. You're going, because you have two substituents from equal distance, then you're going to be going for lowest total. Okay. Same direction. Where are we? Let's say we have a branch substituent. Oop, sorry, I gotta make a little space here. What if we have branching in a substituent? I'm gonna have to erase this all in a second, so I have some room here. What that might look like is do an easy one. Okay. In this case, the longest parent chain does contain 1, 2, 3, 4, 5, 6, 7 versus 1, 2, 3, 4, 5, 6. So this is our parent chain. So we can go 1, 2, 3, 4. That's the attachment point for the substituent. We could call this, since we have the common name, we could call this isopropyl. So this could be 4-isopropyl 5, 6, 7 heptane. But let's say we don't have a common name for it. What you do when you don't have a common name, or you need to use the nomenclature rules, is you always number from the point of attachment. Moving away. So this is our 1 carbon for the substituent. In this case, we would also find the longest chain, but this is symmetrical, so we can arbitrarily use that one. So this is a 1-methyl ethyl substituent. So this would be 4, and then you just use some parentheses. 1-methyl ethyl heptane, or 4-isopropyl heptane is okay too. But if this was 1, 2, 3, now we wouldn't be able to use the common name, and this would be a 1-methyl butyl, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decane. I don't think so. 1, 2, 3, 4, 5, 6, 7, 8, and that one's got 10. 11?
From the top.
Oh no!
Yeah.
Oh, I ruined it! I broke the example.
Oh no.
Sorry.
This example sucks. Well, if Mr. Smarty Pants wasn't so smart, it was a great example, but now it's a terrible example. Good catch. There's no more adding on. This example is broken. This is what happens when you try to just make up examples in the middle of OChem sometimes. So, but you guys get the idea. So, if you have a complex substituent that is actually a substituent, unlike in this example because it became part of a parent chain, then you get the opportunity to name it using nomenclature rules with a bracket and substitute it with an ill designation. Yeah?
Do you have a dash after the parentheses, or you just put it in with no space and catch it from prior?
After parentheses, no dash.
Cool.
So what happens if we've got some, oh, geez, this one, pay attention. Let's see, what if we do this? One, everyone take a shot at naming this thing on your own real fast. And everyone should start be asking themselves a question, which one's the parent chain right now? And this is a new rule, so I don't want to get you guys too far into it because everyone's brain's working on this problem. Is that the parent chain, or is that the parent chain? Let's say
Because it has the substitute group closest to one at the end.
if you have two possible parent chains that have the same length, you go with the one that has the most substituents. So whenever you have equal two options for parent chains, always identify the one with the most substituents. Yeah.
Would it not be 3 options with starting on the?
That's symmetrical, so it doesn't make a difference.
Okay.
Because free rotation here, these are chemically identical.
Okay.
Didn't you write?
So this would be 1, 2, 3, 4, 5, 6, because this chain has a methyl group and an ethyl group. Versus if we use this one, we would have a single isopropyl group. So because we have multiple substituents, it gives you more ease of defining the structure, because you're almost always reducing the complexity of your substituents.
So A is the parent chain?
A is the correct one. So this would be,
But wasn't the third rule you listed earlier, like if more than one substituent, you go with the lowest total substituent?
so that's, this is to identify the parent chain. You have two possible parent chains that have equal length. It's not which side are we numbering from.
Oh, right.
So that's why we're numbering from this side, because methyl's right there on this side. We don't have anything over here on the 5-6 region, which is why we're coming in from this way for our numbering
So
scheme.
that would be a modification to the first one, to be if you want to find the parent chain, go with whatever one.
It's not a modification.
Another part of finding the parent chain
Yeah.
is, the one that will give you the most substituents.
If you have two parent chains that are identical.
Two identical parent.
Yeah. Yeah, it doesn't matter if you don't have two identical parent chains. You stick with the simple ones first.
If two identical lengths, then go with the most substituents out of the parent chain.
Yeah.
And then you can use the numbering rule based on.
To number the parent chain on the base exact, because once you have a parent chain, you can apply the rule for numbering it because you've identified it.
So 1 methyl,
2. 2 methyl, 3 ethyl. Which one comes first alphabetically? So it's 3 ethyl, 2 methyl, hexane.
Can you write the rule out?
Yeah, I don't want me to write the rule out.
Can
That's like that's a lot of my arm.
Can you summarize it again?
If you have two possible parent chains that are of equal length, and you need to figure out which one's the parent chain you're using to name, you'd use the one that has more substituents attached to it. So in this case, this parent chain has a methyl and an ethyl, and this one would only have the isopropyl. Yes?
Okay, so you may have already explained this, but can you repeat again why you put one by the A instead of that other one? That's
Because they're identical.
So,
If I took these, because this bond can turn, and flipped it, it's the same thing.
so then for our purposes.
So it's arbitrary. This could be one, and this could be the methyl.
Okay.
It doesn't change the name.
Right.
It doesn't change the structure. There's no differentiation between those
So
two.
if I in my notes went the other way, it's totally okay. Okay. I just wanted to clarify for sure that that's.
Yep. If you labeled that as one, and this is the methyl on the 2 carbon, you are still correct. This is the most I've ever been interrogated while doing nomenclature. This is good. Most of the time people are sitting there nodding, which is rarely good in OChem.
So the name of it, is it 2-methyl 3-ethyl hex?
Go alphabetical so the ethyl comes first. So it's 3-ethyl 2-methyl.
And then
You said alphabetical order?
Yeah.
Okay.
So you number them based on their location in the chain, but you list them based on alphabetical order. Let's make this more exciting. Because straight chain alkanes, much too easy. Much too easy. Let's go with cycloalkanes too. So cycloalkanes, there's just a handful that we're going to actually work with any frequency, and 2 of them are going to use up a vast majority of our time for cycloalkanes. We have cyclopropane, which is a 3-membered ring. So this is just CH2, CH2, CH2. These are not super common because they undergo significant ring strain. These aren't. They're possible, but they're high energy. Because they have so much strain in this bond. Remember, all of these are tetrahedral. They want to be 109.5. This is planar, and these are 60-degree bonds. That's significantly compressed from 109.5. So it's fairly easy to break these bond and do ring opening reactions with them. That said, they are a thing that we have to pay attention to occasionally. So slightly less strained, but still fairly strained, we have cyclobutane. And then we've got our 5-membered rings, cyclopentane, and then we've got our 6-membered ring, cyclohexane. And you can get larger ring structures, but as we get larger ring structures, they get a lot more flexible and they're a lot less common. And it's really, for instance, when we have in nature, let's say, something that looks like this. We have, let's see, 6, 7, 8, 9, 10. Most of the time, there's a tendency, if you have any functionalization, to close that ring with a reaction. Not always, but commonly. So because of that, these larger ring structures are less common. Yes?
So the cycloprefix just refers to the ring structure?
Yes, exactly. So because it's closed ring, it's cyclic and therefore cyclo. Now, one of the things that happens right out the gate with that, though, is you'll notice these are all CH2s. There's no terminal CH3 on any of these structures. So we don't have any primary carbons or primary hydrogens as part of these rings. Let's see here. So the ring is going to always be named as the parent unless there's some alkyl chain attached to it which has got more carbons. So if we had something like this, The cyclopropane wouldn't be the parent. The 1, 2, 3, 4, 5, 6, 7 heptane would be the parent. And this would be a cyclopropyl modifier of the 3 carbon.
Can you say that rule again?
It's just like finding the parent chain. The one with the most carbons is the parent. So if there's something, if you have a cyclic system that has fewer carbons than a potential parent chain, it's going to be a substituent. If we have something like cyclohexane, 1, 2, 3, and it has an isobutyl group, because there are fewer carbons in the substituent than there are in the ring system, this will be named as a cyclohexane that's being modified versus being named as a isobutane that's been modified. Yeah?
The first one was called 3-cyclopyl. 3-cyclopyl heptane.
Cyclopropyl. So you always just drop the ane and throw an il on.
Cyclopropyl.
Yeah. Anytime you're using an alkane as a substituent, you just drop the ane, put YL on it, and you're good to go. So that's the first rule. Second rule. If you have 2 different substituents, you're going to list them alphabetically, and the number starts on the first one listed. This is a little bit of a trick. Let's make this super easy. Let's address kind of an obvious question here. What's our number here?
1.
Does it matter? It doesn't matter. When you have a single substituent on a ring, if I redrew this over here, is it the same thing?
Yeah.
Yeah. So when you only have a single substituent, we don't number it because it doesn't matter. You can draw it unambiguously without that number. And we typically don't include numbers when something's unambiguous in the nomenclature, just to make it easier. So let me redraw. Now it's not unambiguous. Now we have to find a way to number these. So we're going to list them based on their alphabetical order first. So this is a methyl, this is a propo. So LMNOP, M comes first over P. So this would be a 1-methyl 3-propyl. Notice I numbered in a way that got my substituents the lower value. I didn't call it 1-methyl 2, 3, 4, 5-propyl. It's 1, 3. So this would be 1-methyl 3-propyl cyclohexane.
Could you have done 3-methyl 1-propyl cyclohexane? Or
3-methyl 1-propyl.
Start with the propyl.
No, because we will list these in alphabetical order, and we're going to give the first one listed the 1 designation. Yeah. What if we have another one? What if we had ooh. What if we had a methyl, an ethyl, and a propyl?
1 ethyl, 3 methyl, and then 5 propyl cyclohexane.
We start with the.
So we've got an E,
Start with the propyl.
we've got an M.
So in this case, since we can go in alphabetical order, I'm going to assume we just rotate in the alphabetical order.
So this one's a little tricky. We're going to list them in the name in alphabetical order, like we do with the other alkanes. But we're going to number in a fashion that gives us the lowest possible total for all of our substituents values. So 1, 2, 3, 4. Because the sum of 1 plus 2 plus 4 is 7, and that's going to be our lowest possible total value of substituents. Versus 1, 2, 3, 4, 5, 6, which would give us 1, 5, 6, 11. Or if I went this way, would be one more also. Yes?
Why did you start there instead of starting at the FL?
Going this way? Because, let's see here.
Because I thought it was alphabetical order.
It's
Start
in,
out.
when we write the name out, it'll be in alphabetical order.
Oh.
But for this scheme, because we have more than 2,
Mhm.
we're numbering in a schematic that gives us the lowest possible number for a total for our substituents.
So the alphabetical.
The alphabetical applies for 2 only. When we number with what starts first arbitrarily, we're going with alphabetical, but that's only for 2. So this is going to be alphabetically, ethyl will come first. So this is going to be, or excuse me, methyl. This is ethyl. For ethyl, let's see here. Which one's next, methyl or propyl? So 2 methyl, 1 propyl, cyclohexane. And from this, you could easily draw it. You're like, oh, okay, I've got a cyclohexane ring. I can arbitrarily number 1, 2, 3, 4, 5, 6. 4 ethyl, bang, bang. 2 methyl, got it. 1 propyl, done. You can come up with the same structure from the name. Even though it's drawn differently, it's the same thing. Yeah?
Okay, I did not catch why we are not starting with 1 on the ethyl group versus the last example when you said list in alphabetical order. So we have a methyl and a propyl. So we put the 1 next to the methyl on the last example.
Because if we were to label this as 1,
Well, no, the ethyl is 1 because.
oh, the ethyl is 1?
Yeah. Because it's following the alphabetical order rule.
Is this just for more than 2 substituents? The other one was for only 2 substituents, right?
Yeah.
Yeah.
So for
Okay,
only
so-
2.
Yeah.
That last example is for only for pairs. Whenever you have more than 2 on a ring structure, you have to go to this.
Which is what?
Because-
Why did you start with 1 on
Because
the propyl?
1 plus 2 plus 4 is the lowest possible sum.
Where is it
Ah.
from?
If we started over here and went 1, 2, 3, 4, that would be 8,
Okay.
which is 1 higher than 7. My. Everyone feeling pretty good with this so far?
Yeah.
Okay, let's do some. Oh,
I should have wrote it down.
oh. Let's do. I might be. Everyone's been thinking, man, if you could just chunk this up like other books do, that might be better. Let's do alkyl halides. Let's do alkyl halides. The thing is once you get the base rules, it's just modifications.
Yeah.
Most of the heavy lifting is done now.
I said modification earlier.
Yeah. Okay, so alkyl halides. Or haloalkanes is another. This is when an alkane is modified with a halogen. We still name it as an alkane. And this is the difference. So this is the difference between a functional group and a substituent. These are substituents, which means they modify something being named as something. So because we're naming this base chain as an alkane, it's not being named as a halo something. It's being named as an alkane that's been modified with a substituent, which happens to be a halogen. Functional groups, by definition, change the name. So we'll name something as an alcohol because it has an alcohol group. We'll name something as an amine because it contains an amino group.
How do you determine like what's a substituent and what's a
Just pure by definition. So this is halogens are substituents,
okay.
and alcohols and amines will be functional groups. So they're named as substituents of alkanes, which means all of the rules for nomenclature apply from alkanes. So we just need to add a couple different changes. So if you have a fluorine, chlorine, bromine, or iodine, this is a fluoro group, chloro group, bromo group, or iodo group. So let's just do one. Okay, so we have a bromo group and we've got a methyl group on 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 hexane chain. What side do we number from, the right side or the left side? Right side, because substituent is closest to that end of the chain. So 1, 2, 3, 4, 5, 6. So this is going to be 2 bromo and a 4 methyl. Which one comes first? Bromo, because of alphabetical. So this is going to be 2 bromo, 4 methyl hexane. Not bad. It's exactly like the other ones, except that we added a couple new substituents that aren't alkanes to the party. What about this one? Always throws people because what these mean is you have methyls at every location. So first thing, how long is the parent chain? 5, yeah. Because that's a carbon, that's not. A lot of time people start counting the chain all the way to the end as drawn, and that will get them in trouble. So, do we start numbering from this side, or do we start numbering arbitrarily from this side, even though we could start here or here, and it would be the same thing? Why? Because it's on the first substituent, on number 1. So we have a 1 chloro and we have a pair of 4 methyls. So this would be, what goes first, the chloro or the methyl? You are correct. Okay, that doesn't apply. And remember, because this is going to be dimethyl, the di does not factor into the alphabetical. So let's say that these methyls did have priority over chloro alphabetically, with the, well, let's say the di did, but it doesn't. But if it did, it doesn't apply because di doesn't factor in. It's just the actual name. So this case is going to be 1 chloro, 4 dimethyl pentane.
4
You always have to designate where both methyls are in the di because it could be a 3,4 dimethyl or a 2,4 dimethyl. So you always designate where those are.
So the full name, can you give it again?
1 chloro, 4 dimethyl pentane.
And those prefixes, it's the same thing where it doesn't factor in alphabetically for any of them, or just penalize.
For the bi, tri, tetra, di, tri, tetra, it's universal. There will be other prefixes that will come across later where they are factored in. We don't know why. Because if you look at the IUPAC rule book, it's about this thick. It's just utterly terrifying when you get into carbon, like 30 and 40 carbon compounds with rings, and it's just, thankfully there's software that can name things now. So, yeah.
So instead of fluoro, if it was fluoro, for example, it would still be 1 fluoro 4,4-dimethyl if the dye doesn't follow the
Yes.
rules? Okay.
Exactly. Well, if following the rules, it's just not, the rule says that it's not taken into account for the alphabetical priority.
Yeah.
Okay, stop. All right. Whew. Man, nomenclature is so fun. It's not, it's okay. Anybody's really having a great time with nomenclature? More power. Ethers. Oh, yeah. Okay, so there's some common names for ethers. We use a lot of common name, and you just, so an ether is whenever you have an oxygen, and on either side of this oxygen, there's some carbon and some carbon. I could just call this some R group and some other R group. That's an ether. So, just a sec. So, common names are really simple. If you guys have heard of diethyl ether, that's because there's an ethyl group and an ethyl group. There's methyl ether, which should technically be called ethyl-methyl ether because of alphabetical rules. So if you can neatly name one side and the other side and say ether, you can pretty much nail every common name for an ether. Now, as these get more complex, we have to have other rules for priority for naming these, but common names on ethers are super straightforward. We had some questions down here. Yes?
So is it no longer an ether if there's something else attached to the oxygen instead of one of those lone pairs?
Oxygen likes to have 2 bonds and 2 lone pairs. So the second we start attacking things here and putting a positive charge on that oxygen, we're going to be finding ways to push electrons to satisfy that positive charge. In other words, it's not going to be very stable. So ethers are reactive. So I wouldn't, no, we're not going to be naming these yet. We had another question down here first, but yeah.
The one on the left is called ethyl-methyl ether.
Ethyl-methyl ether. And the book has a lot of different common named ethers in the table, but I'm not going to go through all of them because they're super easy.
Are they generally symmetrical?
No. No, generally they're not symmetrical. The common ones are often because they're small, but as we get into larger ether structures, they're not. Yeah.
You just list them alphabetically.
So if you need to name a larger structure because it's modified by an ether, you change the name to oxy from ane. So if you were modifying, let's say we have something like, I'm going to make something funky over here. We now have an ether. And we're not going to common name this because we have this large structure over to the left. So what this is instead of methane, it's methoxy. So this would be a methoxy group. And you can do this with any alkane. It can be an methoxy, ethoxy for 2, propoxy, butoxy, pentoxy, etc. A lot of the time you see these shorter modifications. You see methoxys and ethoxys pretty commonly. So if you see something like this, you're just going to treat this just like any other substituent and name it as a methoxy group. So this would be, let's see, this is another off-the-cuff thing. So would I label this as 1 because it's closest? Yeah, 1, 2, 3, 4, 5, 6, 7, 8. So we have an octane. So we have a 6-methyl. We've got a 4-ethyl. And we've got a 1-methoxy. Alphabetically. Ooh. Methoxy is alphabetically before methyl. So this would be 4-ethyl, 1-methoxy, 6-methyl octane.
It's not methoxyl, it's methoxy.
Yeah.
You said 4-methyl, 1-methoxy, 6-methyl.
4-ethyl, 1-methoxy, because the O becomes for the Y, 6-methyl.
Why would you put 1-methoxy? It's on the other
Because
side
it's
of
the 1 carbon.
But it's on the other side of the oxygen.
That's not part of the parent chain. The oxygen's not part of the parent chain. This is a substituent modifying a parent chain.
Okay.
Sorry, it was 4-methyl, 1-methoxy.
6-methyl.
Octane.
Octane. Yeah. Okay, let's see where we're actually at here. Best laid plans. Oh my goodness! Okay, so here's what the deal is. We didn't do alcohols, and we haven't done amines. But we really want to spend as much time possible on cyclohexane rings next class. Like, we want at least 45 minutes in cyclohexanes, which means we're going to have to go fast through alcohols, amines. So it sounds like a lot of people are unfamiliar with these rules. Perhaps they weren't reading the book before lecture, which is like what most people do. I would strongly recommend getting into the nomenclature section of the chapter, run through it, look at the examples, make sure you focus alcohols, amines before, because we're going to go quickly on Wednesday with alcohols and amines so we can get to the cyclohexanes. See everybody next week, or Wednesday.